Good morning, guys. We're going to do our first question on erratic motion. Remember, the erratic motion, it means that our position cannot be defined by a singular continuous function for the entire path, right? So the position here will be determined by a series of functions. So meaning a certain function for a certain time interval and a certain function for a certain time interval. And that happens because the motion does not it changes basically. So your motion changes even though it's still along the straight line, but it changes. So the relationship of position against time will keep on changing, right? This happens when things like acceleration happen, slowing down. So that is the changing of motion, right? Those are the things that we can look at in our erratic motion. So we cannot determine the position using a continuous function, right? And also, if you look at this graph of ours, they say a bicycle moves along a straight road such that its position is described by the following graph. Construct the velocity time and acceleration time graphs for 0 is less than or equals to time less than or equals to 30 seconds. So that is the time interval that is given to us. And then right on this graph, I might have left that out, but then for the first region, this is it up until 10 seconds and then up until 30 seconds, right? So you can read the question again and see what is happening there. So they say construct the velocity time graph and acceleration time graphs. Looking at these graphs of ours here, we can tell that this is erratic motion because the position time graph changes, right? Okay, I made a mistake here. This is not velocity, this is position, right? So I'm gonna say S in terms of meters, right? And that is our time there. So looking at this thing right here, I can notice one thing that, okay, for the first part, for the first 10 seconds, my position function is S is equals to T squared. So meaning that it's a quadratic function, right? That's how the position changes with respect to time. But then now when we get at 10 seconds up until 30 seconds, the change, it becomes a straight line, right? So meaning that they have a linear relationship now for the second part from 10 seconds to 30 seconds. So that's why also we have to consider that. So we have an erratic motion here which changes at 10 seconds. So let's see, we have those two functions. They want the VT and the acceleration time graphs, right? So let us remember one thing here. What do we know? What we know is that in our erratic motion, which is our kinematics that we're looking at here, we know that the relationship between the velocity time graph and the position time graph is in this manner. V is equals to the rate of change of position. That is the definition of velocity, rate of change of position, right? Of which this is the case. And then now in this case, this is an instantaneous rate of change, right? They change at this instant. This is how we can write this thing. So looking at this equation, how can I get my velocity from a position time graph? So right, we can see that for the first part, right, which is from 0 is less than or equals to time less than or equals to 10, right? From this point, this is a bracket there. Also here, this is a bracket. It's not a 1, it's a bracket. So for this region, let us see what is going to be our velocity. So velocity, it is going to be, we said ds dt, meaning we are taking the derivative with respect to time of the position time graph. So s is equals to t squared. So the derivative of s is equals to t squared is going to be 2t. That is the derivative of t squared, right? That is me saying ds dt, it is equals to 2t in meters per second. So already I have my first equation, right, for the first region. Now let us look at the second region. For the second region, we're still using the same thing, right, because still velocity time graph from position time graph. So what do we have now? Okay, I'm making a mistake. So it's starting at 10. And remember, this 10 is included in both our functions because it is still it is the start of the second function and the end of the last function. So that's why I'm including it here as well, right? The 10-second part. So meaning that when you put in 10 seconds for both equations, you should get the same value, the same y value, right? That's just the case here. And if you can look at it, let's put in 10 at t, that is 100. If you put in 10 here at t, that becomes 200 minus 100 and then becomes 100, right? So that's just fine there. 30 seconds. Let's see. So now what is going to be your v? Your v is going to be equals to, remember, the derivative of 20t minus 100 is just going to be 20 meters per second. So you see it's a constant, right? So this is the second equation. They all comes from ds/dt. So knowing that relationship in these erratic motions, as long as you know your relationships of your kinetics, of your geometric aspects basically, which is your position, velocity, and acceleration, and then knowing those equations, you can easily get these graphs of yours. So here we can get our velocity time graph because already we have the two equations for the two time intervals, right? So we're going to start down here and sorry. Cool. And then what I'm going to do is I will start having that 10 here. Okay, I might have to take it up a bit. So that I can have the 10 here. And then I can have the 30 here. All right, and then what's going to happen is that for the first part here on our velocity, when I put in 10, that's going to be 20. So that means at 10 to 20, that is also a linear relationship. So I'm going to measure 20 for my velocity. So let's assume this is 10, 20, 30, 40, 50. Right, so I'm going to say this is my 20 in terms of velocity because this is my velocity in meters per second. Right, I'm going to use a different color just to make it stand out. Right, so this is your V in meters per second. Right, those are your y-axis, and then here we got our time, which is in seconds. That is fine. So let us see. So it's gonna end at 20, right? And then at 20 it becomes a constant 20 meters per second. So what happens is that this is gonna be something of this nature. It's gonna go up until 10 seconds. Then at 10 it's 20, right? Note that one thing there, that at this, right, you will have this. Okay, now that we've got the first time interval from 0 to 10 seconds, now let us look at the second time interval. This is from 0 to 30 seconds. So I'm going to go at 20 because it's 20, right? And then we know that this ends exactly at 30, right? So that is going to be your case here. So you do have your velocities for the first time and then your velocity for the second time. And then me trying to label them out, I will do the same. Actually, let me use the same thing. So you see under the first graph, it was red. Also here, I'm going to have the same red. Sorry. So that's the first region there. And then the second region, it is going to be that color. Right, that is just going to be the case here. So you know the first region and your second region for your velocity. We've calculated them there on top, right? Now that we have these two, let us get the acceleration time graph. What do we know about acceleration, right? In terms of kinematics, we know that our acceleration, if I were to define it in words, is given as the rate of change of velocity. This is it, instantaneous rate of change of velocity. That's just the change now here. So looking at our acceleration, how are we going to get it? We're going to take dv dt, right? So let's see for the first motion, which is from 0 and less than or equals to t, which is less than or equals to 10 seconds. Right, so for the first part here, our acceleration is going to be, so remember what is velocity? For the first part, it is 2t, right? So the derivative of 2t is just 2. So I got 2 meters per second squared. That is my acceleration for the first region. Let us look at the last region now. What is going to be the acceleration? So acceleration is going to be equals to, this is my last region from 10 seconds less than or equals to t, sorry, less than or equals to 30 seconds. All right, now in this case, we come back here, we look at our velocity, 20 meters per second, and it's a constant. So what is the derivative of a constant? Always 0 meters per second squared. Now, how do I draw this thing? Simple. I just go down here like that, and then I'll go up like that, and that's it. this is my acceleration in meters per second squared, right? And then this is at 10 seconds, then this one is at 30 seconds, right? And then from here going to 10 seconds, acceleration is 2 and it's a constant, so I'm going to come down here and say and measure 2. So let's see, this is 2 up until 10 seconds, right? From 0 to 10 seconds, and we know that it ends here. All right, and then from there the other part, acceleration is 0 for the whole part, right? That's just that here. And then the other one, the area under the first part, it was always red, so we do that here again to show that now this is the region for the first part. And then yeah, that's your acceleration. You got it now. For the second part, it's 0. So this is your erratic motion. It's just like that. As long as you remember these relationships, and you remember also going back from acceleration to velocity, it's an integral. Going back from velocity to position, it's a integral as well. And also knowing that the area under this thing right here is your it is your velocity, right? The area under a curve is your velocity. And for the second part, if I were to take the integral of acceleration at 0, you know the integral of 0 dt, right? This is just gonna be equals to, because there's nothing here, right? So it's just the acceleration of dt basically, because that 0 now seems like I'm multiplying, but it's an acceleration of dt. There is nothing there, there's no constant or anything. And the acceleration of dt, you know that is just going to be actually, if this was 1, then it was going to be the acceleration of dt, but the integral of 0 is 0, right? Sorry, I'm talking about the integral here. The integral of 0 is 0, but we're gonna have something else here, which means that we will have to have a plus c, because there's 0 there, so we'll have a plus c basically, because this is unbounded, right? And then that unboundedness of ours is gonna give us a c, right? Of which c in this case is a constant. But now let us assume that this thing was right, so that's just the case here. We would get something of this, of which that constant of ours is what is going to be the velocity, which is just 12 in our case here. All right, so yep, that's just the case here. Sorry, it's not 12, it's 20. So it's that constant. So I'm just trying to show you that in an integral we are able to get a number even though we had a 0 here. It's because in an indefinite integral we need to have that c, which is a constant, right? So that's why we add that c as well, so that we can take care of such cases. Because now you see here the integral is 0, so going back to velocity, if you did not know that there's that constant that we get rid of when we are taking an integral, then you would be kind of confused. Why do we have a value here for velocity, yet here we have an integral of 0? All right, so that's just the case, is that c that we're taking care of in indefinite integrals, which gives us that constant velocity now for the second part. Okay guys, let's end it here, and I'll see you on our next examples, right? On also on curvilinear motion. Thank you.